So my name is Ammar Bakhurji. I'm an APC engineer, part of a centralized engineering group in Aramco for doing APC, RTO, and advanced solutions. So today I will try to share with you some of the AI use cases that we do in under process control and optimization, and the outlook of Aramco in terms of future trends for autonomous operation. So we'll start with the introduction, and then I will try to provide some process and control and optimization. How does it fit inside autonomous operation? Then I will share 4 examples of actually using AI in our operation. And finally, concluding by comparing different approaches and providing some of the future trends that we see. So start with Aramco, as you know, is one of the largest oil producers. It's an integrated energy and chemical company. We operate below the surface, and our operation is very diverse, as you see in the graph here. We cover below the surface exploration, also until the terminals and chemicals as well. My department specifically is located in the headquarters of Aramco, which is in Dhahran, and specifically in this building you see here in Dhahran, Saudi Arabia. It's called the Midra Tower. And as I said, we're part of an advanced process solution group that are responsible for the deployment of solutions across our mainly kingdom assets. These include solutions such as APCs, in which we have more than 550 applications. We also monitor our base control assets. We have more than 20,000, and we use technologies such as CPM or control performance monitoring to ensure that these assets are actually utilized and effectively utilized. We also deploy real-time optimization or multi-unit real-time optimizations across our facilities. We have more than 3 implementation, and more is planned. And also, we also are responsible for implementing AI and machine learning into process control and optimization. This is a trend of how the journey has been so far for autonomous operation. So, as you know, we started in the 1980s for building the infrastructure of automation, which is basically the instrumentation and connectivity that allows our data to be able to be controlled. In the decade after that, in the 1990s, we had our first APC implementation. And then the decade after that, we focused more into scaling the APC applications. These include not refineries, but also NGL fractionation, gas plants, and what have you. And because of that and of the large deployments, we built our APC best practices and APC standards. The decade after that, which is 2010 and 2020, we started seeing data mining techniques. So we focused more into performance monitoring of all our assets of APC and base layer using technologies, as I mentioned before, like control performance. We looked also not into novel applications of applying APC for our conventional oil fields. We also looked into early adoption of machine learning. In that time, we had OT and IT integrations, and also we come up with Aramco digital strategy around around 2019. And then from 2020 until now, we are focusing more into real-time optimization technologies, or basically closing the gap between our planning and actual operation. And we do this using technologies such as multi-unit real-time optimization, reinforcement learning for advisory optimization, and we're looking into utilizing more of generative AI as well as machine learning inference. So just to reiterate, so what I will try to do in the couple slides is try to see how process control and optimization contribute to our journey toward autonomous operation. And then also we'll provide some comparison between AI that we keep hearing about and the conventional approaches that we are used to do. So I think Mark has already mentioned the different level of autonomy that are a maturity level of autonomous operation. Basically here, what I want to leave you with in this slide is when looking at autonomous operation, we need to focus on the roles that we're trying to automate. So I gave an analogy here between self-driving cars, which has the role of a driver, and the actual plants in terms of the role of the board operator. So you see for level 2, for example, where we are supposed to have occasional autonomy and human always responsible and specifying intent, looks like adaptive cruise control in cars. Basically, when you specify the set point and the car will take care of the speed. And actually, for our facility, that looks like APC. It's doing the same thing, the operator is just providing intent, but the APC is taking care of that automation. So similarly, we see these conventional technologies as already taking us closer to level 3 and level 4. But the more we go, like level 4 and 5, going back to Mark's point, is it worth it or not? So that's what we're trying to talk about. Okay, so before I move into the applications and give you some example, I just give you some basic information. As you know, machine learning, there are 3 main types of machine learning. Supervised learning, where we have inputs and outputs, and the machine is asked to find out the algorithm that perfectly describe that relationship. And supervised learning, when we have data and we ask the machine to find patterns. Similar example of this is clustering. And finally, reinforcement learning, which basically an AI agent that acts on an environment, and based on rewards, it's able to learn how to behave, basically, and interact with that specific environment. And in the field of our process control and optimization, we do have conventional approaches and mature technologies that are already available in the 3 domains I'm showing here, which are process control, process optimization, and soft sensors or inferentials. We have our own advanced regulatory control, which is still used, very mature. We have also model predictive control, or APC. These are one of the mature technologies for process control. What we have as emerging in the same field, we're seeing RL, or reinforcement learning based process control, and we're also seeing ML and AI model-based control. For process optimization, we have real-time optimization, or RTO. For emerging approaches that we are seeing more use, also similarly using of reinforcement learning for optimization, and also surrogate models for optimization as well. Yeah. And for soft sensors, the old, very robust method of regression, but we're also seeing more use of machine learning and AI models for predicting soft sensors. Okay, so now I'll move into the applications. I'll start first with this application of AI. The challenge we have here is that when we wanted to deploy our APC for our oil field, we have very large number of oil wells. And each oil wells, in this case, has like submersible pump, valves. So by itself, you can think of it as a unit. So to do APC, as you know, we have to do step testing to generate the models. But doing a step testing for 400 different wells is just too much of a task. So what we have done here is basically we capitalize on clustering algorithms for machine learning. Using the data of those oil wells, we worked with our reservoir engineers and production engineers. We got all the data for the wells, including depth, some static data about the pumps, everything. We combine it together and we run a clustering algorithm, and we were able to define a finite number of clusters. In this case, it's 5 clusters. And instead of just testing everything, we just tested some samples from each of these clusters, and we built the models accordingly, and we used it. So this has led us to 80% reduction of our testing time, and being able to produce, to install APC on those 400 oil wells, which resulted also in tremendous savings in energy. For the second application here, basically, typically for optimization, we do have some application or some facilities in our operation that they are not very linear in terms of optimization. The optimization targets are not linear. So APC cannot help in that situation because APC mainly is for linear optimization. So what we're targeting here, those facilities where having a full-blown RTO is an overkill or more expensive or is not economically feasible. So an APC is not capturing all the benefits. So we look for something that we can use that will capture this non-linear optimization that are not non-frequent. So it's not as frequent as a typical refinery where the target changes, but these type of applications, the target does not change frequently. So for that case, we used a reinforcement learning based optimization. And the idea here is that we capitalize our already existing simulation models for all of these facilities. And we run that reinforcement learning agents on this simulation thousands and thousands of times for it to be able to learn that physics and understand the process. And then we ask it, we avail it to our operator and engineers as advisory for them to use, to advise them on the most optimal operating point for them to use. And we have seen benefits, improved profitability for those, and being able to capture that additional benefits. And we also have enhanced energy efficiency as well. Third application here is, in Aramco, we manage a very large network of gas oil separation plants. It's a very complex and very large network that has facilities, pump stations, and very, very different kind of, all connected together in a very complex way. And what we're trying to do here is trying to optimize that network in a near real time to be able to react to any issues as fast as possible. And doing it for rigorous models, which is the typical approach, is to build a rigorous model for all those facilities, will be very high. You require very high compute to run those optimization, especially being dynamically mixed integer optimization, which consume more compute and very difficult to. So what we used here is we try to simplify many of the models whenever is applicable to using surrogate-based models to make the compute easier. And we were able to run this optimization and achieve our optimum targets using this hybrid approach of surrogate model and rigorous models. This led to reduced also energy and as well as reduced emissions. And the final example I'm going to show here is implementing of reinforcement learning. But in this case, we are actually implementing it at the DCS level. So this process specifically that I'm showing here is for amine treatment units. Typically, we use advanced regularity control to control it. Some facility, they use APC if it's economically feasible, but usually it is at the borderline. Typically, we use ARC. So we wanted to test the use of reinforcement learning for actual DCS because we believe autonomous operation is not real until you close the loop. So we keep hearing a lot of AI solutions, but we want to try closing the loop actually in the facility and see how will that help us. So this is actually a pilot that we have done, and the initial results are very promising. We're seeing better control compared to having an ARC. And we see continuous learning, which is actually very promising because this will reduce the need to retune, right? Usually process control engineers, they typically check the controllers or retune it, or even the PID tuning may not be, it has to be robust to capture all the nonlinearity. But for this case, the RL is able to have that continuous learning and nonlinear control as feed condition changes. And we have seen that it has a better handling of mild process upset as well. So initial results are promising. However, we're still monitoring it and we're still keeping time, and we want to see how does it evolve over time and how we see the control. Is it going to decrease with time or is it going to improve? Okay, so we talked about different approaches, as I mentioned before, and in this slide, I'm comparing it in terms of several factors. The main issue that we have with the black box approach or data-driven approach is explainability. So to bring those AI solutions closer to your plant, explainability is key. So that's why we always try to combine physics-based with our AI to give it some kind of explainability. So this is one point that is important for us, and for that reason, we often prefer having a more gray box approach or white box approaches rather than doing like full-blown black box approach, or use black box whenever it's applicable. Similarly, maintainability is an issue. Having a black box, it makes it difficult to maintain. And similarly, if you have physics-based, it requires frequent updates and frequent maintenance. But having both, you might get the best of both, and you will not need as much maintenance as having a physics-based approach. And we want to also to capitalize on the ease of deployment of AI solutions, especially with MLOps and with the things we have seen for ease of deployment. Having both best of the world maybe will take us also, allow us for ease of line optimization. Okay, so in terms of future trend, I'm going to share some ideas and some trends that we keep hearing about and something that we believe it's interesting. So I'll start with AI and ML and APC. And we're seeing APC vendors are offering integrated AI ML features within the APC framework. And we believe this maturity will grow, more will happen. And also, example of this can be also using machine learning for inferentials or hybrid models for APC and RTO. A bit not available yet, not mature, but I think it is coming. It's using use of AI agents and generative AI. Generative AI will become commonplace. We're going to start seeing it more. But I think one of the biggest benefits of having generative AI is to use it for, in the framework of APC, is as an assistant role for knowledge enrichment, and especially for APC design, deployment, and maintenance. For those three areas, it's provide, I think, the best benefits. Similarly, if you can look for DCS and PLC, where you have not as much new knowledge, we'll keep losing a lot of people with TDC 3000, for example. You don't find as many people, but Gen AI will be able to. You can use it for programming, especially these difficult to learn languages, or not. We don't have that expertise anymore, or we lack it. Multimodal features also, we think it's going to be commonplace. We'll start ingestion more different types of data rather than only relying on time series. We'll use multimodal like drawings, best practices, standards, operating manuals, and what have you. And for our autonomous operation, I think the key thing here is handling startup and shutdown. I think so far we are with APC, RTO, and the existing technology, we're at the very good level of level 3 or 4, 3 maybe. But having like a startup and shutdown automated also, that will take us a step closer. We also keep hearing in the conference in agentic AI for handling specific situations. And also a very interesting concept that we recently heard about is operator digital twin. So we keep hearing about digital twins of your assets, which are facilities, but in this case, it's the actual operator. You have a digital twin of your actual operator that will ensure your tribal knowledge is maintained in that specific digital twin of the operator. With this, before I conclude, most of what I mentioned here in terms of applications, we have done in a joint white paper with Motiva, talking about most of the applications as well as the approaches that we have for APC and RTO. And it is published in the Computer and Chemical Engineering Journal. This is the barcode if you are interested, if you wanna read it. Thank you, and that's all. Back to you.